Let's talk about quantum computing. First of all, quantum computing is nothing more than using quantum mechanics to do some kind of computation. So how does it work? We have some kind of system, quantum system, and that system has some kind of state at some point in time. And that state can change according to some kind of time evolution. You're probably thinking, oh no, I need to know the whole quantum mechanics just to do this topic. But turns out it's not that difficult, because you don't need to know all the continuous functions like that, and all the states, how they change in time, all the differential equations. No. We can limit ourselves to basically only two-dimensional systems, which means we're only gonna use zeros and ones and everything else that comes from them. We can combine them, but the idea is that it's only two-dimensional system, so it's only zeros and ones. Okay, it still might sound difficult, so let's look at an example in classical system. Basically in classical computer, how the computation works using the same notation as we're going to use for quantum computing. So we're going to look at an example. We're going to look how your phone or computer works right now, how the computation is done. So we also have a system, so basically your computer would be some kind of system, and it would have some kind of state. So you can imagine state would be like a screenshot, and then that state changes. So basically the screenshot changes every millisecond or something, and you get a video. So let's talk about that. So our system is a computer, and the state would be ones and zeros. Simple as that. We have some kind of ones and zeros. So it could be just 0, just 1, or it can be a combination of those. So 0, 1, 1, 0, for example, or 1, 1, etc. So for now, for this kind of computation, we're gonna use this notation. It's called bracket notation. This is called a bra. No, this is called a ket. And for one, we're gonna use this. And for anything else, we're gonna use same thing, just in one ket. So these kets are nothing more than just vectors. So what is a vector? Well, I guess you can learn it yourself, linear algebra basics, but vector would be just like a few numbers. So 0 in our case would be 1, 0, and 1 in our case would be 0, 1. Now, what do we do with, for example, 1, 1 or 0, 1? If we have more than one bit in this case, this is a bit. If we have more than one bit, what we're gonna do is called tensor product. Tensor product. That we're gonna notate it as this symbol, cross. In LaTeX it would be O times if you're using LaTeX. So 1 and 1. So it's gonna be 0, 1, tensor product 0, 1, and tensor product, what it does, it basically picks the first vector and then multiplies each entry with the second vector. So this multiplied by 0, 1, this multiplied by 0, 1, and we get 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1, 1. And you can do the same thing with 0, 1. You can try it yourself, pause the video. Now I'm gonna show you. Tensor product. Again, now it's gonna be 0, so 1, 0. Tensor product 0, 1. Again, picking the first one and multiplying by the second one each entry. And we get 1 times 0, 0, 1 times 1, 1, 0 times 0, 0, 0 times 1, 0. Here you go. You can try yourself with also with 1, 0 or with 0, 0, and you would see that actually what this does, it's really simple. You don't need to do actually these kind of computations each time, because let me pick another color. If I can do that. No, maybe no, I cannot. Whatever. So basically this is a binary number 3. This is a binary number 1. And if we look at these numbers and we start counting from 0, this is gonna be 0, 1, 2, 3. And as you can see, we get the third number 1. Here we're gonna get 0, 1, 2, 3. And our 1 is marked as 1 because this is the number 1. So yeah, basically write all zeros and choose 1 for some kind of entry. Yeah. So this is how we do classical, how we can encode our classical state, our system. Yes. Let's continue now with evolution. What does it mean to have some kind of evolution? For evolution, we're gonna use operators. Examples, for example, basically these operators work in all the computers, and it's enough to have 3 of those to do basically everything. Let me write those down. Not, or, boom, 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 and would be 1, 0, 1, 0, 0, 0, 1. Here you go. And what are we gonna do? We're gonna multiply. So basically, if we want to show the evolution, we're gonna change the state. Oh, you usually see these as diagrams like this. Boom, boom. In electronics, if you took some courses in electronics or something like that, and then you can show like make diagrams, connect those, like, oh, make this connection and this connection, and so on. So we can do the same with matrices. As you can see here, we have matrices. What we can do, we can pick a matrix and multiply it by the vector. Let's remind ourselves how matrix multiplication work. So let's pick this example. Have matrix like this, and we multiply by matrix like this. 6, 9, 7. So we're gonna pick here the row and here the column, and multiply 1 by 1, and then add them together. So it's gonna look like this. Three times 3 plus 7 times 1 plus 5 times 5. And then do the same with others. For example, we can pick the second column and here the first row, and then again do the same thing. So now we're gonna have a number here. It's gonna be 3 times 4 plus 2 times 1 plus 9 times 5 and so on. And we get another matrix. Yes. So let's do that with an example. In basic electronics scheme, it would be having 1 and then doing the NOT gate. How does it look? For our notation, it's gonna be NOT 1. Let's expand it. NOT is this matrix. 1 is this vector. Now let's multiply. 0 times 0 plus, okay, this row, this column. So it's gonna be 0 times 0, 1 times 0, 0. No, I messed up. Yeah, sorry, it's the opposite. We're multiplying the row here and column here. So it's gonna be 0 times 0 and 1 times 1. Yeah, forget about it, the previous thing. 0 times 0, 1 times 1. So it's gonna be 1. And then 1 times 0, 0 times 1. We add those and get 0. And this is nothing else than 0 vector. Yeah. Another example, we have AND 1 0. So AND gate, let's remind ourselves, is basically giving us 1 only if both bits are 1. In this case, 1 is 0, so we should have 0. And let's see how it goes. AND. Yeah, AND is 1 0 1 0 1 0 0 1. And then we have this thing, 2-bit vector. So we're gonna have a column like this. 1 0 is 2, so it's gonna be 0 1 2 3. And now we're multiplying. 0 times 1 plus 1 times 0 plus 1 times 0 plus 1 times 1 plus 0 times 0. We're gonna have 1. Then 0 times 0, 0 times 0, 0 times 1, 1 times 0. It's gonna be 0. And yes, we got 0. Woohoo! And the last example with a little bit longer circuit. Yeah, it would be having 0, applying NOT, having another 0, and then applying OR gate, like this. And we're gonna write it as OR NOT 0. Tensor product 0. So our OR gate is 1 0 0 1 0 1 0 1. Our 0 vector is 1 0. Oh, sorry, the NOT gate, right? NOT gate is 0 1 1 0. 0 is 1 0, and then tensor product 1 0. There we go. You can try do it yourself. I'm actually well, I can show you. Yeah, I can show you. Let's start with this thing. 1 times 0, 0 times 1, 1 times 0, 1 times 1, 0 times 1, 0. So we're gonna get, let's rewrite this thing. We're gonna get here 0 1, which is just 1, and 1 0, which is 0. So 1 0 is 2, so this should be 0 1 2, like this. Zero, 1, 2. And again, multiplying. 1 times 0, 0 times 0, 0 times 1, 0 times 0. So this is 0, and 0 times 0, 0, 1 times 0, 1 times 1 plus 1 times 0 is 1. And we get 1. So this is how computation is done with classical computers. Yes, simple as that. We have a system, we have a state, and we change the state by using matrix multiplication. Now, you could also practice doing these things with other circuits like half adder, but this notation is not very common because actually it's not used in electronics or something, because it's only zeros and ones. It's really cumbersome to do something like that. So we use like basic circuits and basic notations for that. Only zeros and ones. We don't need matrices for that and vectors. And but you can try yourself with so-called half adder. Half adder, what it does? Half adder. Let me pick. Yes, half adder. What it does? Basically implements the XOR gate, which called like this, which basically picks NOT and the other normal thing, then takes this as a NOT, this normal thing, makes AND, then does OR. So we can practice this with this circuit, for example. Also do the same thing, but let's move on. Now, what does quantum computing do in this situation? Quantum computing, let me pick this. Quantum computing actually can be more than just 0 and 1 and 1 0. It can actually be any number in these places. It can actually be a complex number even. Negative, positive, complex, whatever. So, as an example, we might want to have something in between 0 and 1. So if we have a so-called NOT gate, as we looked before, 0 1 1 0. What it does, it basically well, how did I write those matrices? Basically, you can just enumerate 0 1 2 3 and decide what each vector would do. With each vector, what this matrix would do. And if it's OR gate, then it's gonna be 0 for 0, which is 0 0, then 1 for 0 1, 1 0, 1 1. So we's gonna have 1, so it's 1. So basically you can just go through all the columns and see and write like in order. So the same thing is here. We have 0 and 1. 0 becomes 1, 1 becomes 0. And what we can do, we can make it so that 0 would become 1, 1, and 1 would become 1 minus 1, for example. It could be any numbers, like this. Bam. Whatever numbers you want. And we can see what happens if we pick this and, for example, the 0 thing. If we multiply 1 times 1, 1 times 0, it's gonna be 1, and then 1 times 1 minus 1 times 0, gonna be 1. As you can see, it's not 0 and not 1, it's something in between. So this is actually called a superposition of 0 and 1. Superposition. So if we would light a LED or something, so in the classical system it's gonna be, if 1 it's gonna be lighting up, if it's 0 it's gonna be not lighting up, and in quantum system it would be sometimes lighting up, sometimes not lighting up. So there's some kind of probability. In this case it would be 50-50. Sometimes it's lighting up, sometimes it's not, because our state is in a superposition of 0 and 1. So yes, and but yeah, if we want to somehow measure the probability computed, then for probability we want all the cases to add up to 1. And in this case, if we have a rule to square these things and then add, basically we would have probability 1, that's not nice. So in that case we need to normalize it. So we're gonna have some kind of normalization. So we're gonna compute the norm. So the norm would be 1 squared plus 1 squared. Norm squared. Norm squared would be 2. And our norm is square root of this, so square root of 2. So this is the norm of 1, 1. And yeah, if we want this to add up to something like that, we want this to be 1. Yes, we want to be this 1. So because this is a probability, this is also a probability, we want to add it to 1. So we're just gonna divide by square root of 2. So this should actually be 1 over square root of 2, 1 over square root of 2, like this. And yes, and this is gonna be called the Hadamard gate. Now, in classical system, it's really easy to implement these things. If we have 1, it's basically LED or some kind of bulb, and it's lighting up. If it's 0, it's some kind of LED or something like that, and it's not lighting up. And if we want to do some kind of gate, some kind of evolution, then we can implement that with transistors. This is gonna be the output. For input we can have switches, and the switch would be on. Here the switch would be off. This is gonna be the input. And then we can do some kind of circuits with transistors. For example, the AND gate would be transistor here, like this, and then we have here, so this is gonna be one input, another input, and then output, like this. This is the battery plus, this is the battery minus. So yeah, and then we can put here some switches. We can put here a lamp bulb or LED, like that. This is gonna be battery minus, this is gonna be battery plus, and we can have a circuit. We can then combine those gates and do computation. This is actually how our computers work, but of course we're not using basic transistors. We're using some really small things, but they are in principle working as transistors. So yeah, so it's easy to imagine how it works in classical system, but how does it work in quantum system? So in quantum system, we're actually gonna have there are multiple things how we can implement computer. Actually, the same thing with classical computer. You can find some videos where people even using like dominoes, or they're using like water to do computation. So you can actually do that, not with electricity, with also other things. So the same with quantum computers. You can also have multiple implementations. So one implementation is called photonic computer, and as an example, the ones and zeros would be basically photons. So we have some kind of light particle, photon, and it's going boom 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 boom, and or we can just not have a particle. Then there's nothing here, then it's zero. And then we can have some so this is basically an apparatus that's emitting a photon. So we have some kind of photon emitter. Well, you can buy it. It's like some kind of device that reduces the light to one photon, which is quite difficult actually to do, but you can do it. And it's gonna be one photon flying out. Then you can have this thing called so it's gonna be a 1. This thing called beam splitter, which is basically just a mirror that is not reflecting all the light, but reflecting 50-50. So some light is going past, some light is reflecting. 50-50. Beam splitter. And then you can have some detectors, also detecting the photon and telling you if the photon is received or not. So this is the photon detector. And you can have the same thing here, also a photon detector. And then it's gonna tell you 1 or 0 if the photon is detected or not. And so yeah, and this thing would be, in our example, the Hadamard gate, the H box. H basically, as we've seen above, takes some kind of number, 1 or 0, and it makes a superposition between 0 and 1, 50-50 chance. So it's the same here. We have 50-50 chance that our photon is gonna be reflected or gonna go through the beam splitter. So this is how it works. So this is one of the examples. Yes. So now let's look at more computations. So we have a Hadamard gate. We have a Hadamard gate, which is like this, turning 0 into 1 divided by square root of 2, and 1 is becoming 1 minus 1 with square root of 2. Then we have X gate, which is basically the NOT gate as we had before. Then we have Z gate, which is doing nothing for 0 and changing 1 to 1 with a minus. So it would seem that it doesn't do anything. Like if you measure the probability is gonna be again 50-50. The same. This is not gonna change anything. 50-50. So not 50-50, but I mean if it's 1, it's gonna still be 1. Like that minus sign doesn't do anything because we square it. But actually it does, and this is called also a phase gate. Phase gate. Now what is the phase? We can see the phase also here. The phase is basically, you can imagine it as sign difference between 0 and 1. We have state 0, we have state 1, so it's gonna be some kind of superposition of those, but we can imagine that it's not gonna be just sum or difference or subtracting, but it's gonna be some kind of thing between that. We can add, we can subtract, we can do something else. So yeah, between 0 and 1, the sign difference. And we can see that with this way of turning some kind of 0 or 1 of whatever state, I'm using the letter psi, and we can express it as this. Cosine 0. Wait, let me write it with a bit more space. It's gonna be e to the power I gamma cosine theta 2 0 and then plus e I phi sinus theta over 2 1. So this is called the global state, global phase, and turns out it doesn't matter what it is. Yeah, it doesn't matter for computation. It matters if it's like an intermediate state, but if we're measuring or something like that, well, yeah, it actually doesn't matter either way. In intermediate or final state, the computation is the same, because how would you understand it? You could have 0 plus 1, 0 minus 1, or you can have 1 minus 0, sorry, x minus y, or y minus x. It's gonna be the same thing. Yes, it's the same thing, because we can write it as a minus in front. So this would be like a global phase, and then yeah, it will be the same thing, because we only care about the sign difference. So 1 is plus, 1 is minus, doesn't matter which one. And yeah, this is the so-called sign difference between those. So this is our local phase, not global but local, or just phase, that actually matters. And as you probably know, e to the I pi is minus 1. So in this case, z is nothing else than phase gate that applies phase pi. Yes, we apply pi phase. So this is the phase, and we get minus in front of the 1. Yeah, so that would be a short explanation, but we're gonna look into that a little bit more. But for now, yeah, this is how you can imagine. So another gate that I forgot to mention is the CNOT gate, also an important one. I'm gonna write it like this. 1 0 0 0 0 1 0. This is the CNOT, and let me repeat the other ones quickly. Qiskit, Z-gate, and what it does, so yes, so Z-gate, as I told you, for 0 it doesn't do anything. For 1 it becomes the phase 1. For X is just the NOT gate, so 0 becomes 1, 1 becomes 0. Then Hadamard gate, if we apply to 0, it's gonna be something between 0 and 1 with A plus. We can also write it as this. And if we apply 1, it's gonna be 1 over root of 2, 0, minus 1 with the phase. We're gonna write it as the minus state. What does CNOT do? It's called the control NOT. So we can write it as something as a target here, and this is gonna be a control. What does it do? If this is 1, this is flipped. If it was 1, becomes 0. Was 0 becomes 1. If this is 0, nothing changes. 0 stays 0, 1 stays 1. And as you can see here, we can see that 0 0 stays 0, 0 1 stays 1, 1 0, because this is 1, changes to 1 1, and this is 1 1, and it changes to 1 0. Yes. Example, CNOT 1 1 becomes 1 0, like that. Let's do some more computation. Let's take a 1, then apply a Hadamard gate, then apply an X gate, and then apply a Z gate. So first of all, 1 applied to Hadamard. Hadamard is Hadamard 1 is 1 over root square root of 2, 1 1 1 minus 1, 1 is 0 1. Already did that, and we get 1 over square root of 2, 1 minus 1. But now we're gonna apply X gate to this thing. This is not 0, not 1. So we're gonna use the matrix notation immediately, because we don't know how to write it. Well, we know we said it's like minus thing, so we're gonna write it as a minus state. Now let's write matrices 0 1 1 0, and then 1 over square root of 2, 1 minus 1. So 1 over square root of 2 stays as a scalar. Then we multiply 0 by 1, 1 by minus 1, we get minus 1. 1 times 1, 0 times minus 1 is 1. Yes, so we just put the minus up. So it's basically minus state. And now we apply the Z gate to the minus state. So again, it's gonna be nothing to 0 and minus for 1, and then we're taking times minus 1 over square root of 2 minus 1 again 1 over square root of 2, 1 times minus 1, 0 times 1, so it's minus 1, and then 0 times minus 1 times 1, it's gonna be minus 1. Yes, so this is just minus and a plus state, like this. And this is our answer. We could also write it all in one thing. We apply h to 1, then apply x, and then apply z. You can actually multiply this as matrices. You can multiply those matrices and multiply by vector all together, and we're gonna get this thing. Another example. Now we're gonna have something with a CNOT. We're gonna have this circuit. Apply Hadamard, then apply CNOT, target qubit is the first one, controlled qubit is the second one. Then see where it goes. This is gonna be our psi 1. This is psi 0. Then we're applying Z gate, and then this is psi 2. Then we're again applying CNOT and Hadamard gate. I'll see what it becomes. So first of all, Hadamard to 0. Hadamard to 0 is plus, which is 1 over square root of 2, and then 1. When we apply CNOT to this thing, but we're gonna apply CNOT for our state, so it's 1. And then also this thing, so we're gonna have a tensor product with 1, 0. We're gonna tensor it and see what do we have. CNOT. CNOT 1, so it's gonna be 1 over square root of 2, and then 1 and 1 was 1 and 0, 0, 1 and 1, 1 and 0, 0, like this. So as you can see, it's something between in the middle of 0 and 2. Not 0, not 2, but something in the middle. And then we apply the CNOT gate, so it's gonna be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. times 1 over square root of 2, 1 0 1 0. So we're basically picking the first thing. Our first thing is 1. Oh, don't forget this thing. So gonna have 1. Sorry, 0. The first thing is 0. And we're picking also 2. So the 2 is this thing, and this is 1 0, right? No, it's 1 1. And this is 0 0. 1 1. Like this. And we're adding those together. This is this thing, this is this thing. So we're gonna have 1 0 0 1, like this. And this is our this state, psi1. Yes, and let's continue with another example. Not another example, let's continue with psi2. Now we're applying Z gate to the first qubit. How does it look? Psi2. Gonna apply Z to the first, and for the second nothing, it's gonna be identity. So we're applying Z to the first, and again tensor product can be also with matrices. Identity does nothing to the second qubit, and we're applying this to our psi1 state, this thing. Yes, so it's gonna take the first qubit, this one, and gonna apply Z gate to it. So let's now not do the tensor product. You can try it yourself, but now let's try switching to the more easier notation. We're not gonna use matrices anymore. We're gonna use the bracket notation like this. So instead of using this, we're gonna write like this, and then we can use linearity. So for this thing, we can just write it as 1 over square root of 2, and then we apply Z to the first qubit. To the other we don't do anything, and do the same for this. Apply Z to the first qubit part, and do nothing with another, like this. So we got Z here, and when we do linear algebra, right, we can distribute Z. So now Z to 0 is 0, so nothing changes, and then Z to 1 is minus 1, so it's gonna be minus 1, and another is 1, like this. So as you can see, Z changed our phase. It was plus and it became minus. Yes, and this is also sometimes written as phi plus, if I'm not minus, if I'm not mistaken. But let's forget that for now. And yes, and now we're at this state. So what can we do now? We can apply CNOT and then Hadamard. We can do those both in one go. Apply CNOT to the psi2 state, and then apply Hadamard to the first qubit, second leaving alone, multiplying those two and applying the state. So again, CNOT to this state, it's gonna be 1 over square root of 2, and then let's see, 0, so it doesn't change. 1, so we change this to 0, so it's gonna be 0 0 1 0. Now apply Hadamard to the first qubit. For the second we do nothing, so it's gonna be Hadamard to the first, second nothing, minus Hadamard to the first, second nothing. Right. Now Hadamard to 0 is plus. Hadamard to 1 is minus. You can actually put this behind the parentheses. It's just like basic multiplication. So it's gonna be 1 minus plus minus minus, and then 0 here. Right. And now what we're gonna do is, wait, this is just 1 over square root of 2, and then 0 plus 1. This is the same just with minus, right? So we can write it out. Because this is 1 over square root of 2, this is also 1 over square root of 2, we can write it, we can extract it here, multiply, so it's gonna be 1 over 2. So yeah, 1 over 2, and then this is 1 plus 0 plus 1, this is minus 0 minus 1, so 0 minus minus is plus 1, and then we have 0. So this is nothing more than just 0 minus 0, nothing, 1 and 1, it's gonna be 2 times 1, 2 times, so we just gonna multiply it by the half, and it's gonna be just nothing, 1. Simplifies, so it's gonna be just 1, and we have 0, like this. And as you can see, there's no superposition, nothing, it's just 1 0, always. If we measure it, it's always 1 0. Right. And we could actually also do the same thing without the Z gate. Then it's just gonna give us the same thing again, same thing back. It's gonna be 0 0. You can try it yourself. So yes, we're using linearity for all this stuff. So actually, oh, let me fix this. Like that. Yes. Okay. So let's look at other cases. What we can do is let's draw the diagram again. Like this. Now we can apply actually not Z, we can apply X gate here. Like that. So in this case, we already know what state is this, right? Psi1. Psi1 is nothing else than 1 over square root of 2, and then 0 0 plus 1 1, right? and then we apply the X gate. So X gate does what? X gate, this in this case changes only the first qubit, so X, and for the second qubit nothing. So it's gonna be for the first qubit X gate, second qubit nothing, first qubit X gate, second qubit nothing. Which is X gate is just NOT, so 0 becomes 1 and 1 becomes 0, like that. We can try the same thing with X and then Z. What if we apply Z? Then we would have Z and identity to, let's call this psi2. Again, we're gonna now apply Z to the first qubit, so it's gonna be Z to 1, which is -1, right? Applying phase. And for 0 we do nothing, so it's gonna be just this thing. As you can see, just a phase difference between those signs, the same thing as it was before, right? Z is a phase gate. And then again, can do the same thing and apply the CNOT and Hadamard. So let's do with the last one. With this, let's apply CNOT and Hadamard. First CNOT and then Hadamard. This, let's say this is psi3. So firstly CNOT, so for the first thing doesn't it changes because it's 1, so it's gonna be 1 1. This is 0, so it doesn't change the second one, so it's gonna be 0 1. Then apply Hadamard. So well, wait, we can do it better. Oh sorry, this is 1 over square root of 2. Can do 1 over, we can write this as 1 over square root of 2, and then let's put minus in front, minus 1 over square root of 2, right? And then can do it like this, 1 minus 0, right? And 1 in front of it, right? This goes outside, and we change the signs by putting minus in front of it, like this. Now this is just the minus state, right? Or we can just leave the minus like it was, right? And we can just change these. So it's gonna be 0, minus 1, and 1 in front. Now this is the minus state. And Hadamard to the minus state is what? It's 1. So we get 1 1, like that. Again, we did some calculations, and yes, and this is not superposition, this is a pure state, 1 1. Now let's summarize what we got. We had one circuit which was like this, 0, then 0, Hadamard, CNOT, and then we can apply nothing. I'm gonna put it like this in the box. We can apply X gate and we can apply Z gate, or only one or neither, and then we can again apply CNOT and Hadamard like this. And in the case of nothing, so identity, we just get back to 0, 0. In the case of X gate, we get 0, 1. In the case of Z gate, we get 1, 0. In the case of both X and Z, we get 1, 1. Now the middle state for each one of those, the middle state here is, here it's just 1 over square root of 2, 0, 0 plus 1, 1. Then this is, for X, is just 1, 0 plus 0, 1. Here it's just phase, so 0, 0 minus 1, 1, and this is the X gate with the phase, so 1, 0 minus, well, it was 0, 1 minus 1, 0. Okay. So if we look at these things, these and these actually doesn't matter if we measure. If we measure, we're either gonna get both, sorry, I mean this and this. It's gonna be both zeros or both ones. Here also both zeros or both ones. Because we square it, the probability is this number squared. So minus 1 squared is just 1, and then times this, so squared, which is 1/2. The same here, 1/2. So it doesn't matter actually if we measure at this point. The same thing goes with other two. We're either gonna get 1, 0 and another 1, and or 1, 1 and another 0. Same thing here. So yes, from measurement point it doesn't matter. And also this is called the entanglement. We achieve entanglement at this point because now if we measure only the first qubit, 0, for example, it becomes 0, then the second qubit must be 0, and we can just bring those like a long distance from each other. And if we measure the first one, the other must be 1, cannot be 0. So the state collapses. So it's the same thing with others. If we measure this 1, another must be 0. If we measure this 0, another must be 1. But that's it. So why do we need those minuses and pluses? So this is the thing about the phase. We had an angle, which was the theta angle. Basically, we can choose the probability of 1 and 0, right? So that's called a superposition. So for superposition, it's basically choosing the probability. For example, 50-50 between 1 and 0. So we can actually see that. We can just put the lasers, the photons, and put the mirror, and then see that 50-50 chance is we're gonna have a photon in one place or another. So it's easy. We have superposition, but what about the phase, the Z gate? So the phase actually can also hold information, and you can imagine it as being something intermediate. So we can have it like this, some kind of state 1, then apply Hadamard gate, we get then the minus state. We can apply Z gate, when it becomes plus state, and then I can again apply a Hadamard gate, and now it's gonna be 0. Of course you could say like, oh wait, so we can just flip it, 1, NOT gate, 0, and that's it. Yes, it's true. The same thing is with, if we have Hadamard gate and then apply Hadamard gate again, we're gonna just get the same 1, so we can just not do anything, and it's also gonna be 1. So, but yeah, so it's true. But the thing is that with this thing, we can show that we can actually hold information in a phase, because at this point, if we measure here or we measure here, it's the same thing. It's gonna be 50-50, 1 or 0. But actually, if we apply Hadamard gate, then we see that it actually matters if it's minus or plus. So yeah, so that actually matters if we measure it before or after. So the measurement can not distinguish the thing, but if we apply something more, we can actually extract the information. So the same thing goes here, right? We have here some kind of superposition, and we apply phase, and this phase change actually shows some information. This holds some kind of information, and then we apply again some gates, and you can see that it actually differs, this thing from this thing. This is 0, 1, and this is 1, 1. So it turns out we can actually encode some information with this, and you can imagine that this is some kind this is like a one person, like Alice. This is another person, Bob. We usually call those Alice and Bob in information theory. And you can imagine that they pick 2 qubits, they entangle those with these states, and then this guy just leaves to another side of Pacific Ocean, or goes to another galaxy, and this person stays on Earth. And then this person on another galaxy can do those gates, can do nothing, can apply X, can apply can apply Z, or can apply both. And this way that person encodes these 4 states. One of those is like both, depends on whether both are zeros or both, or they are different, like 0, 0, or 1, or 1, 0, 0, 1. So one thing is, do those bits are different? Are those bits different? Another thing is the phase, if the phase is minus or plus. And we can encode that, and now all you need to do, all that person in another galaxy needs to do, is send that 1 qubit of his. He sends that 1 qubit back to the person on Earth, and he can apply this thing. He can apply those gates, and he can see what was changed. So he can basically, by sending that 1 qubit from another galaxy to this, you can actually send two classical bits, and that is called the superdense coding. And that's it for today. Thank you for listening, watching. I hope this makes sense, and see you in the next tutorial. we're gonna talk more about algorithms. So yeah, that's it. Bye.